Hello everyone, this is going to be our class for January 19 of 2024. So initially we're going to start with a review on lesson 3A and 3B to just take into account some of the things that you should be doing for your practices. Notice that we've been extending the notion of what we can represent points on. Initially, we could represent points on the unit circle, and now we're going to represent points that are in circle of radius r, with r as our arbitrary number. So in class, we got that if we have this this circle of radius r, with a point P over that edge is going to have coordinates r cosine of theta, r sine of theta. Okay? This is coming, of course, from having a relationship with the unit circle, where if we have a triangle here, and let's say this measures 1, this is the unit circle, and this is r, and in the unit circle we had that this was cosine of theta, and this part was sine of theta. So x was cosine, sine was the height. And for here, let's say this is A and this is B, by doing a relationship of similarity of triangles, so this big triangle is similar to this small triangle, we can have that r over 1 is equals to A over cosine. So with that, we can find that A is r cosine of theta, and in a similar way, we can find that B is r sine of theta. Okay, concluding that the points can be represented in this way. Now, if we use this for our exercise from yesterday class, we have a Ferris wheel, and that Ferris wheel has an angle theta that is describing in what position the gondola of the Ferris wheel is. We're interested in different positions. Initially, we're going to be interested in the gondola when you board it, so which is pretty much here. Notice that when you're boarding, your angle doesn't exist, so there's a 0 angle in there. So you can use what we previously got, and for the initial coordinates, we essentially have 40 cosine of 0. And we have 40 sine of 0. Now, cosine of 0 is 1 and sine of 0 is 0, so we have 40 dot 0. And this is going to be our initial coordinates for this point. Now, if we want to get to point 1, and we assume that that angle is 60 degrees, we do a very similar thing. But now we're going to change the angle, of course. So we're going to have 40 cosine of 60. And we're talking about here degrees, right? So make sure that you have your calculators in degrees when you're following this. The cosine of 60 will give you 1/2. And the sine of 60 will give you square root of 3 over 2, if you remember your special angle class. So this will be giving me the point 20. 20 is square root of 3. Now, for question C, we want to make a plot of the height, so pretty much the y coordinate here, that describes how the movement of the gondola is. So if you recall, we're essentially what we're doing is we're going in a circle, we're going in this direction. We're going in this direction. We're doing this movement. And so, of course, we initially start with a 0 angle, then we get a 90 angle, a pi angle, or 180 over here, and 270, and then 360 or 2 pi. Okay. Okay. So notice that, of course, if you start plotting points, you're gonna find out the 0 is here, that we get to the highest point when it's pi half, that we get to 0 again here in pi, and then we get to the lowest point in 3 pi half, and then we're back to the origin in 2 pi. So this gives me a regular sine function. Let me try to actually draw it here. Could be better, but this works. Now, however, for an engineer, it doesn't work out having the Ferris wheel in terms of angles. He is more useful to the guy to plot it on time versus the height. So it turns out that the Ferris wheel completes 2 revolutions in 6 minutes. So if it completes 2 revolutions in 6 minutes, it means that probably 1 revolution takes 1 minute, takes 3 minutes, sorry. And half a revolution is going to take 1.5 minutes. And then a quarter of revolution is going to take 0.75. So that means that to get here to the top is 0.75 minutes. To get here is going to be 1.5. To get here is 2.25. And to get here finally is 3 minutes. So that's precisely the type of question that this is asking. So it says for what values the Ferris wheel will be at 0. And so this starts, of course, at t equals 0, but also at t equals 1.5, t equals 3, then 1.5 more 4.5, and then 6. This will be the points where it's touching 0 here and here in terms of height. Now, in what values will be at top of the gondola? So top is here. Is 4.75, so 0.75 minutes, and also 3.75, which is 0.75 plus a full turn of 3 minutes. On the other hand, to reach the bottom of the gondola, it gotta be 2.25, which is the initial point where it gets to this point, and then 5.25 as well. Is 1 full turn again, and that's gonna help me out to have enough points to plot this one. So we have 0, we have 1.5, we have 3, we have 4.5, and we have 6 in terms of the zeros. And for the top, we have 0.75, so here, and 3.75, so here. For the bottom, we have 2.25, so around here, and 5.25. And that'll be enough to make your graph. As you notice, this is gonna be a little bit more faster than what it looks like before. So your sinusoidal function should have a graph like this. And this was terrible. Cannot plot with this tablet. All right, but that's the idea. So you probably gotta make a better sinusoidal function, but that's the idea. Now notice that the period of this is the difference between 2 maximums or 2 minimums, right? So if you do the difference between these 2 maximums or these 2 minimums, you're gonna find out that the period is, of course, 3. As it makes sense, well, full turn is 3. The amplitude is given by the radius of the Ferris wheel, which is 40. And notice that a general function that describes the Ferris wheel is gonna be given by f of t equals 40 sine, remember this is amplitude sine of speed times t. So sine, and we have the period, but we don't have the speed or the frequency, so we can just remember the formula that Rayleigh does. So the period is 2 pi over b, so that means that b is 2 pi over the period. Since the period is 3, so this means that this is 2 pi over 3. Okay? And so that is the function that completely describes this movement in terms of time. Now let's move on to 3B. Now for 3B, we have a different scenario. We have radar maps. From those that can be used for aircraft control towers or weather reports. And they have, of course, a shape of a circle. So in here, we can use the same type of coordinates to locate points at different stages. But what we want to see here is that we can vary a little bit of the distance of the radius even if we are going over circles. So in radar screen, such as the display, you have special markings on them. In this diagram, it shows that this line divides the circle into 8 equal parts. So if you're thinking, well, if this divide in 8 equals part, how much is this angle pieces that we have over here, like this piece and this piece? And that's easy to find out. Essentially, the only thing that you need to do is take 2 pi, which is the whole thing, and divide by 8. So if you do that, you're going to get that this measure is pi over 4. And now, given that that is pi over 4, or 45 degrees, this means that this other angles here is 45, and between each of the lines is a 45 degrees angle. Now, one question that arises is, if you suppose that an object traveled outward from the center along one of the lines through the origin, we want to know if the radius increases, decreases, or stay the same, and what happens to the angle is increasing, decreasing, or stay the same. So what's happening is this, like for example, let's assume this line in AB, and an object is traveling here, it's here, 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 here. So it moves along this line from A to B. So what happens here, of course, is that the radius is going to increase, but the angle theta stays the same. That's when I'm moving along one of the lines. Okay. Now, let's check how some of these things behave. So let's suppose that the outer circle has a radius of 30 miles. So this outer circle here. And a remote control drone travels from point A to point B in a straight line. So it's coming from here to here. It's traveling to a constant speed, and it takes the drone 80 minutes to make the journey. So let's create a table that matches that scenario that we have here. We have a 0 is a distance of 30, then at 40 is a distance of 50, and then at 80 it finally reaches the point B. Now we can calculate what is the distance from L to this horizontal line L here. And that, of course, is going to be like the height coordinate. So we can measure this in terms of sine. And so what's going to happen is that we can use the angle that we calculated before. We know that this is pi over 4 or 45. So we know that this being the initial distance, this can be calculated as 30 sine of 45 degrees. Or you can use pi over 4 if you're using radians. This is going to give you a result of 21.2. Similarly, you can do this here, 15 sine of 45. Notice that the angle is not changing. The only thing that is changing is the radius. And so finally 0 sine of 45, and well, 0 is 0, so this is just going to give me 0 in distance. So if we were to sketch this here, notice that when we get to 80, we're going to reach 0. And so we have this point here. And initially, when we are at 0, we have 30. So we can kind of make a line between those 2 points. Okay. And this is going to be the graph that represents that. Now let's consider a different scenario, and now the lines that's divide over here has a equals par again, and the other circle has a radius of 30 miles. But instead, let's consider an object that is travel counterclockwise along one of the circles. So it's going through here. Let's say it goes here, 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 here. It keeps moving over here, over that circle. So what is going on with that? So here, does the radius increases, decreases, it stays the same? What happens to the angle? So here is the opposite situation from before. Since we are not changing the circle, the r stays the same, but theta changes. We are changing, when we're moving along the circle, we're changing the angle of the position. Okay, and so one example of this will be, suppose a small airplane starts from point 8 and travels around the other circle back to the point 8 at constant speed, and it takes 80 minutes to make this round trip. And so if north points up in this diagram, the sign's distance of the airplane to the boundary line L is the number of miles the airplane is doing. But notice that this is a full circle over here, and this is starting at this point. This is, remember, this is 45. So this is 30.45. This is the 21.2. So if we were to make a graph of this, the sine distance will produce a sinusoidal function. And so that sinusoidal function is going to look like this. Notice that it's a little bit above of 20, so 21.2. And because it's a circle, then it's going to start from there, and it's going to start doing a sinusoidal function. Okay? So those are the two scenarios that you can see in terms of movement for the unit circle. And this concludes our review of lesson 3A and 3B.